Okay, here's our last video for section 5.3. We're going to do example number 5 and then go to example number 7 because we kind of skipped around a little bit. Talking about the fundamental theorem of calculus, part 1 and part 2. If I ask you to take the derivative of this antiderivative, we should be able to use our part 2 of our fundamental theorem of calculus. But if you remember from the other examples, when we found the derivative of the antiderivative, that only worked when we were going from a number up to a variable. And this doesn't say that. This says we're going from a variable to another variable. And so what we have to do is we have to actually make it look like the fundamental theorem of calculus. And so instead of going from negative x to positive x, can I use my rules or properties of integrals to separate it into two different integrals? Can I go from negative x to 0 and then again from 0 to positive x and then add them together, which would be the same thing as going from negative x to x all in one? And why would I do that? Well, I would do that because now I have a number to a variable. Well, in this one, I have a variable to a number, so I've got to switch that around. I have to make sure that I go from 0 up to negative x. But you remember the other rule for integrals? That when we flip the limits, we have to negate it. And so making sure that I use those properties correctly, if I'm going from a number up to a variable and I switch it, then I have to make sure that I add that negative in the front. All right, so now I have an integral that says we're going from a number up to a variable. If this is the antiderivative and I want to take the derivative, well, we know that the derivative of the antiderivative, using my fundamental theorem of calculus, says that I could plug this in to my variable, and then I just have to make sure that I multiply by the derivative of that upper limit. So that's what I have. I've plugged in my negative x into my variable. I've multiplied by the derivative of that upper limit, which is a -1, but then don't forget I have another -1 from the beginning. Again, I plugged in my upper limit, I multiplied by the derivative of that upper limit, but don't forget we have a negative in the front from flipping those limits of integration. Okay? I'm going to do the same thing for the other piece. If I'm taking the derivative of this antiderivative, then I should be able to use that fundamental theorem of calculus that says they're inverse functions of each other. I should be able to take this upper limit, plug it in, multiply by the derivative of that upper limit, which is just 1, and so I end up getting a 1 times x cubed. So in this second piece, I have a negative x cubed. That's a negative x times a negative x times a negative x. That's a negative x times another negative. That's a positive. Times another negative. That's a negative, right? So don't you end up with a negative x cubed plus an x cubed, which ends up to just be 0. All that work for just a 0. But that's how we do it. If there is a derivative of an antiderivative, we have to make sure that it goes from a number to a variable. So we might have to separate it a little bit in order to make sure that we can use that fundamental theorem of calculus. Okay? All right. Last example is example number 7, and this time they took away our equation and they just gave us a picture. And it says here, let g of x be the integral from 0 to x of f of t, where t is the functions whose graph is shown. So the graph they're giving us is f, and f is the derivative of g, isn't it? And so if I take the antiderivative or integrate f, then I will get the value of g. And so we know that the integral of f is really the same thing as the area underneath the curve of f from 0 to x. And so we have a couple different parts here. Part A asks us to estimate g of 0. Well, g of 0 is really the same thing as the integral of f from 0 to 0, isn't it? The integral from 0 to 0, because x is 0, I can plug in 0 to my upper limit, because if I know that g of x is the integral of f from 0 to x, and I know x is 0, then I can plug in a 0 there. And so really, g of 0 is the integral of f from 0 to 0, is the area underneath the curve from 0 to 0. Well, if I've gone nowhere, then the area underneath the curve from 0 to 0 is nothing. It's just 0, right? So g of 0 is 0. Let's do the same thing for g of 2. So if g of x is the integral from 0 to x of f of t, then I can say that g of 2 is really the integral of f of t from 0 to 2, or the area underneath the curve from 0 to 2. It asks us to just estimate, so we can use our picture, kind of count the little square units and estimate the area. And so I ended up getting 1, 2, 3, 4, 5, 6, 7-ish. Would you say that the area underneath the curve from 0 to 2 is 7? And so the area underneath the curve from 0 to 2 is 7, means that g of 2 equals 7. Do the same thing for g of 4, g of 6, and g of 8. G of 4 is the same thing as the area underneath the curve of f from 0 to 4. Counting up all those squares and estimating, I got a value of 9. So g of 4 is 9. I did the same thing for g of 6 and g of 8. Finding g of 6 is really the area underneath the curve from 0 to 6. Finding g of 8 is really the area underneath the curve from 0 to 8. Now be careful. As soon as I go past 4, doesn't that function drop below the x-axis? Which means all of those pieces are now negative areas. And so from 0 to 6, I ended up getting a negative 8 because I had approximately negative 1 underneath there. And that's how it dropped from 9 to 8. The area underneath the curve from 0 to 8, aka g of 8, I ended up getting 5 because I had more negative area to add to my positive area. All right. Part B says find the largest open interval on which g is increasing. Now, if g is the integral of f of t, and I want to figure out where g is increasing, don't I have to figure out where g's derivative is positive? Well, if g is the antiderivative of f, and I take the derivative, right? If I take the derivative of this side and the derivative of this side, well, isn't that my fundamental theorem of calculus that says the derivative and the antiderivative cancel each other out? So really, the derivative of g should just be f of x. Does that make sense? And so if I take the derivative of the antiderivative, I really just get what's inside. So the derivative of g is really f. So if I want to figure out where g is increasing, I've got to figure out where g prime is positive, or where f is positive. So where on the graph is f positive? Well, where on the graph, if this is f, where is he above the x-axis? Well, isn't he above the x-axis from 0 to 4? And so if f is positive from 0 to 4, then that means g's derivative is positive from 0 to 4. And if g's derivative is positive, then that means g is increasing from 0 to 4. Because his derivative is positive, which is the same thing as f of x, I know that g is increasing from 0 to 4. What does part B say? Oh, we also have to do decreasing, don't we? And so if we're looking for where g is decreasing, we've got to figure out where g's derivative is negative. And if g's derivative is the same thing as f, then we've got to figure out where f is negative. And it looks like f is negative from 4 to 8. So I know that g is decreasing from 4 to 8 because his derivative, which is f of x, is negative. All right. Part C says identify any extrema. Extrema means maximums and minimums. And so when the derivative changes from positive to negative, I've just found a maximum. Or when the derivative of g changes from negative to positive, I've just found a minimum. So if g's derivative, again, is the same thing as f, we've got to figure out where there's a sign change. If g's derivative changes signs, aka if f changes signs, then you have a relative extrema. So doesn't f change signs at x equals 4? F changes signs from positive to negative. And so if f changes from positive to negative, that means g's derivative changes from positive to negative. And so that means there is a relative maximum. So I know that there is a relative maximum at 4 comma something, because I know that the derivative of g goes from positive to negative. And the derivative of g is the same thing as f, going from positive to negative, right? Now, relative maximums and minimums are points, so we've got to figure out the y value of this point. We've got to figure out when x is 4 in g, what's my y value? Well, wait a second. Didn't we find that from our first part? Didn't we say up above that g of 4 is really 9? So I can say that I have a relative maximum in g at 4, 9, because g's derivative, aka f, goes from positive to negative. All right, part D says sketch a rough graph of g. Well, I know actually 1, 2, 3, 4, 5 different points, don't you? From part A, don't we have a point at 0, 0, and 2, 7, and 4, 9, and 6, 8, and 8, 5? You should be able to plug in, plot those 5 points, and get a rough sketch of what G's graph looks like, even though you had no idea what G was. Kind of a complicated problem. You might have to go back through there a couple different times, but it's kind of a good check for understanding problem where you're talking about integration, which is the same thing as area underneath the curve. You're talking about the fundamental theorem of calculus, where the derivative and the antiderivative cancel each other out. Kind of complicated, but go back through there, make sure you understand it, and then let me know if you have more questions. Okay, guys? All right, that was the conclusion of Unit 7. We only have one more unit after this. We're almost done. Hang in.